Hello, CCP2 students. This is Dr. Kirshner, and this is Friday's lecture, January 29th, and we're doing some fill in the blank for some labs. We're going to be doing labs number 5 and number 6, and I'll be using my version, but before you get started with this, if you haven't got your lab books out, go ahead and do so right now and turn to experiment number 5. Experiment number 5 is one we couldn't do because we didn't have the right reagents, but we're going to put some data in and do some checking of it. So if you need to get your lab book, stop this video and go get it and turn to experiment number 5. Okay. All right, so rates of reactions again. Okay, rates of reactions depend upon a couple factors. One is how much reactants you have. So if you remember, I'm going to right now, let's see here, go to the beginning of this rates of chemical reactions, experiment number 5. So here's basically a reaction, and you have reactants A and B. The coefficients are A and B, but basically the rate's going to be determined by the concentration of A times B. If you remember, we don't know. Unlike equilibrium, where we would put it to the A power and B to the B power, we don't know these exponents. They're called the orders of the reaction. So what we have to do is actually do the reaction at different concentrations of A and B and figure out what happens. So for instance, if you double A, the concentration of A, and the rate goes up by 4-fold, well then you know that the order of the reaction for A is 2-fold, is 2. So for instance, if you make A twice, but you get a 4-fold increase in rate, 4 is equal to 2 squared. If you increase by 3-fold and it goes up by 9-fold, you got the idea. If you increase it by 2-fold and it only goes up by 2-fold, then you know it's basically order of 1. So that's kind of what we're doing again. You're doing some of these reactions, which I'll give you the data for, and you're trying to figure out the order of the reaction. So that's one thing we're doing. And the reaction we're doing, let's get to it here. There's a lot of theory in this one that they go through, is this reaction right here. Just so you know what it is. It's not on a test or anything. Basically, it's called the iodine clock reaction. Basically, you add, hydrogen sulfite plus iodate. Iodate is IO3 minus. And the reaction runs and you get I2. Okay, I2 is something you can see by color. So we can actually monitor how fast this reaction is by the appearance of a purple color. Turns out if we would have had the right reagents, you can make the color more intense if you add what is called starch. Starch in I2 makes the color even deeper. So the rate of the reaction, we know because of the two reactants, is proportional to the bisulfate or the hydrogen sulfite and iodate. But we don't know the order of which it depends. And so in the experiment today where we do data, we're going to not do this part here. We're going to vary the concentration of this and see what happens to the rate. Does it get twice as fast if we double it? Well, if that's the case, then our exponent is 1. If we double the concentration of iodate and it goes up 4-fold, then it's 2. If we double it and it goes up 8-fold, then it's 3, so on and so forth. So we're actually trying to get this right here. And we're going to vary the amount of iodate in the reaction. So it's really important to find the concentration of iodate when we put our reactions together and then measure the rate. So anyway, this is discussed as if we can take our data after this and graph it and take the log of the rate and take the log of this, we can have then a graph where we can actually look at as it being y equals mx. And if we're taking the log of both sides, basically if we get a 1, that means the order is 1. If we get a slope of 2, order is 2. If we don't see any change in rate at all, it's a 0. So if we actually take the log of the rate and the log of this side, it should equal our n. Our slope should equal n, which is this. So anyway, you don't have to really understand that math, but it's just a way of taking this equation and doing something to the numbers and graphing it so you can see by slope whether your order of the reaction is 0, 1, or 2. Okay? So anyway, we also are doing one other experiment, and that is we're going to use our Arrhenius equation, we're going to show some data in which we do it at different temperatures. So let me show you the temperatures here. Oops. The discussion of it, I should say, temperature. So way back when we did the Arrhenius equation, we had a slightly different form, but you can kind of remember that what we had was we had activation energy over RT times the natural log of the concentration. And this is actually the natural log of the reaction rate. And A, by the way, is some other factor which we want to talk about. Anyway, so this is a form of the Arrhenius equation, which basically, if you have the rate of the reaction at two different temperatures, you can plug it in and find the activation energy. So that might be faintly in your mind. So we're going to end up doing that too. Our main job today, though, is I just want to get started on this. Then I want to finish up lab 6. So the first thing I want to do, let's go to lab 5 and let's do some of these questions. Now, one of the things this does is it keeps your mind, every time we go to this, your mind will remember this more and more. So by the time we get to May, some of these labs we're reviewing will be a little bit fresher than saying, oh my God, I did this in November. I have no idea what's going on. So let's say we have this reaction and we're trying to figure out basically the exponents M and N. So what we do is here's our concentrations of A and B, our two reactants. We look at the time. So what I want you to notice is instead of it putting the actual rate, what I want you to do is see it as 1 over 19 for this one. So in other words, the reaction happens once in 19 seconds. This is 1 over 38. This is 1 over 38. This is 1 over 76. Now, this rate here, let's say this is the slowest rate. This is the slowest rate. Let's put this as x. This rate right here is 2x because it did so in half the time. This rate is 4x. So let's look at this data real quick. So I want to, first of all, we have to translate this into a rate. And right now it's in how many seconds it happened in. So I'm just translating it like we're going to do in our data and say 1 over 19. And that's actually a pretty fast rate. That's a pretty high number compared to 1 over 76. But if you look at this as a fraction, you can see that 1 over 19 is 4 times faster than 1 over 76 and 2 times faster than 1 over 38. Now let's look at what's going on in here. So what I'm seeing here is that B is halved, or you can say B is doubled. So when B is doubled and A stays the same, our rate goes up twofold, from 2x to 4x. So I'm going to say that M is 1. 2 equals 2. You double it, you double the rate. Now let's go over to here and compare these two columns. When we keep B the same at 0.02, but we start out at 0.010 and we go up to 0.020, we also double the rate. So N equals 1. Now if we double both of them, going from here to here and from here to here, if both of them double it, we should get a rate increase of 4-fold, and we do. So I'm going to put a 1 and a 1 here. Okay, so now our total order of this reaction, total order, is now equal to 2. So now if we wanted to figure out this thing right here, what is this thing? Well, what time would you predict if the concentrations A and B were made to be 0.005? We'd be looking at those rate equations. And we would be plugging in the initial concentrations, which is up here, and the final one. So let me look that up real quick. And you can as well. We're going to go to chapter number 14 to look this up. Remember, we never memorize these equations, but they're kind of like calculus-derived ones. But we have to find the right ones, and we have to say, basically, it's a order 2 equation. So let's see if we can find that real quick. Let's see. So this is a second order reaction. So what I have for this, to solve this question, is 1 over the initial concentration, that's I, by the way, equals your rate constant, whatever that is, times time, let's see here. Oops, my bad. This is actually the concentration at a later time. So this is AT. So it's KT times plus 1 over A sub 0. A sub 0, by the way, is the initial. So you can plug all this stuff in. And what time would you predict if it's that? Now, did they give us the constant? And I don't think they did. So, well, anyway, I'll show you how to do it, though. This is a trick question. So you put 1 over the time, the later time is 0.005 equals the rate constant times what we're going to look for, which is T, times 1 over the initial concentration, which is 0.020. Okay, so anyway, where do we get K? What we can do with this equation, by the way, I won't do it here, but you guys can try to solve this, and that is, you're going to plug in A, B, excuse me, and then the rate 1 over 19 and find K. And then you can go ahead and do this equation. So the second question they put on the pre-lab, well, there's actually 4 questions, is we're going to be doing a lot of recipes where we put together stuff and we have to calculate the final concentration of things. So it says we have 35 mils, I'm going to call it 0.035 liters, times 0.0024 molar, which is moles over liter. So so by the way, we're going to then add it to 15 mils of water and 50 mils of this sodium sulfite, persulfite I should call it. Anyway, you're diluting it. So we could do it as a dilution problem, or we could do what I'm about to do. So what's the new concentration? So the initial concentration is 0.0024. Here's my idea of how to do this. We want to figure out how many moles is in the original. So we take this, and this is kind of ugly, but I'll do it with you. Calculator. Okay, so 0.035 times 0.0024 equals, we get 7.2, sorry, times 10 to the negative 5th moles. Then what we're going to do is, let's look at the final volume. We got 0.035 liters. We added another 15 liters, 0.015. We also added another 50 milliliters. That's that. Remember, we have to put this in liters if we're doing molarity. So we got 0, we got 9.09. So put this over 0.09 liters, and then you'll get our... So anyway, once you plug and chug that, if you want to do that, let me see. I'll actually do it right now. Points. We already have the 7.2 on there. Let's divide it by 0.09. We get 8 times 10 to the negative 4th molar. So we diluted a little bit, or as you might call it, 0.0008 molar. So it went down a little bit. It went down by about a third. We have to do those calculations, so trying to do that. So you've done this one before, especially in biology class, a reaction profile. So here's your reactants. That's their potential energy. But let's say we're doing an exogonic reaction where we release energy, so our products are down here. What they want you to realize is that you have to actually go up in energy to go there. Now, if you do a catalyst, this activation energy, as they call it, will go down. So I'll put a little hump here that's smaller. That will increase the rate a lot. Now this one, you have to do a lot of ratios of rates and stuff. Now when you do rates in chemistry, you have to do it per second. Per second. So given this is not really a rate of reaction, it's a rate of travel, we're going to do that. We're going to put it in seconds because that'll be easier. So it says his friends at the engineer club call him Herb the Missile. In June, he rode a 10-mile bike time trial. So it's 10 miles in a time of 27 minutes. So speed is distance per time. Distance per time. So the time, though, has to be in seconds. We can leave the 10 miles there. So we're going to put 10 miles per 27 minutes and 3 seconds. So we have to take 27 times 60. Let's do that. 1620. So 1620 seconds. In 3 seconds. So let's put 1623 then. So 10 per 1623, whatever that is. Next one. He did it a little bit faster. He did it in 25 minutes. So 25 times 60 plus some seconds. So how many seconds is it? 1516. So I'll put 10 miles were done in 1516. So divide this out. Let's do it. 610 divided by 1623. Yuck. 0.0061 miles per second versus, let's do the other one, 10 divided by 1516. 10 divided by 1516 is 0.0065 per second. So it's about, so the rate would be 0.61 faster rate divided, so it would be 0.65 over 0.61. Okay, so now what we would have done in the lab is we would have put together a couple cocktails of reactions with different amounts of iodate. So let me go back to the reaction again. I'm going to be giving you data today, and then I'm going to let you work on some stuff as far as converting it into something we can deal with. Let me go back to the reaction. So you're like, what are we talking about again? Okay, here's the reaction right here on page 4. We're only going to look at this guy. What is the what is the order of the reaction with respect to iodate? So basically in the reaction, we're going to put the reaction with different concentrations of iodate. The problem is we're going to have it in a recipe, so we'll have to figure out the concentrations later that we put in. So let me go to the data and give you the data that you can chomp on. So we did our pre-lab. Okay, here we go. Effective concentration. So first of all, you don't know the concentration yet. What you have to do is later on in the calculations, you will figure out what is the molarity of your KiO3 when you did it in this mixture. But anyway, let me give you the data for this. I can find it. Let's see here. All right. So we did this last year and I kept the data. So 10 seconds for this one. Write that in your lab manual. 15 seconds for this one. 20 seconds for this one. And this one's 26. So again, this page is page what? 11 in your lab manual. So please write that in. And then we did the following temperatures. We did 22 degrees Celsius, 12, and 2. And what we got was, by the way, both ingredients were at the same temperature, so this is kind of a repeat here. So yeah, we're going to say that the temperature for both was that. We got 10 seconds for the higher temperature. That's a fast rate, by the way. 20 and 40. So it kind of, you might say, I can't believe that data. It basically doubled every time we went up 10 degrees. It actually did. Now, the other thing we can do is we can test to see if any chemicals are catalysts. And what happens if you have a catalyst? All of a sudden, the reaction actually goes super fast, like within a second. So what we found last year is that this was a catalyst, and these two were not. And this was a catalyst. So now, with this data in hand, we're going to go over to the calculations. Okay, so what we're going to do, volume, and then we're going to do concentration. So how do we do concentration? So first of all, let's put in the time again. Why not? 10 seconds. This is in seconds, good. 15, 20, 26. Okay, how do we do the concentration now? So let's look at the concoction we did. This is very much like our pre-lab question. We mix 50 mils with 50 mils. So basically what this is then, I want to, we can do this kind of in a shortcut, but let's do it in the long cut. So let's figure out let's go back to our, what our ingredients were and figure out what our concentration of iodate was. Let's see here. Here we go. So here's our iodate. It's 0.0024 molar. So 0.0024 molar. So I had to look that up myself. So we have 0.0024 molar. Okay, so this guy right here, the KiO3, equals 0.0024 molar. In other words, moles per liter. So if we multiply that by how many liters we put in, which is 0.05, we can get how many moles we had. So this is moles per liter. We can get moles out of that. So let's do that. And let's figure out our moles for all of these. So we'd multiply 0.0024 times 0.05. Then we'll put 0.00. We'll put 0.0024 times 0.035. Then times 0.025 and then 0.02. So let's do that real quick. So here we go. 0.0024 times 0.05 equals. So we got 0.000. Whoops, sorry. Let me make sure I got the right number of zeros. Yep, 12 moles. Our total volume, though, for all of these, if you look at it closely on our recipe. Sorry for going back and forth. You notice that these recipes, get out of there, all add up to 100 mils. So they're all in 100 mils now. So we're going to put our total number of moles per 0.01 liters. So all of these will be divided by that. So let me do the division on here. Whoops, sorry. Divided by 0.01. So we get 0.012 molar. Okay, now let's go to the next one. 0.035 times 0.0024. Equals, and divided by, again, 100 mils, which is 0.01 liters. So this one is 0.0084 molar. Okay, let's do the next one. Point 0.0024 molar times 0.02 liters is 0.0048. Lots of zeros, divided by 0.01, 0.0048. All right, and then the last one, just 20 milliliters. Now, one thing you might notice is that this number is roughly about twice that number. Roughly. I'm saying roughly, like it's pretty close. But it's not quite right, so I'm not sure what's going on here. So, okay, let me go back and do this calculation one more time. Let's see here. 0.0024 times 0.05 equals, divided by 0.01 equals 0.012. Okay, let me try the next one again. 0.035 times 0.0024 equals, divided by 0.01. 0.0084, everything's going well. I'm just trying to be careful here. 0.0024 times 0.02 equals, divided by 0.01 equals 0.0048, and then find the last one. Okay, last one is 20 mils, so we got 0.0024 molar times 0.02 liters equals, divided by 0.01 equals 0.0048. What? I am so sorry. Let me try this again. This one is 0.0048. I didn't put 25 in before, so one more time. Sorry about this. 0.025 times 0.0024 equals, divided by 0.01. 0.006, sorry. Okay, so we got 0.006 here. So then what I want you guys to do is take the log of this. This is the log 10 of it. Then I wanted you to take the log 10 of the rate. By the way, it's 1 over time. So 1 over 10, 1 over 15, 1 over 20, and 1 over 26 seconds. So then I want you to take the log of this rate over here. So after you get this in, take the log of it. And then after you get this one, take the log of that. And that you're going to graph this and look for the slope. So you can use your Excel to do that. Okay, next one. Okay, let's put in our data for the temperature again. So the original temperatures, again, this is on the page we put the data, but we're just putting it back down here. 22, 12, and 2. In Kelvin, we add 273 to this. So we got 295 here, 285, 275. I'll let you guys do the inverse of that. Let's take that number and just take the inverse. Time in seconds, it was 10, 20, and 40. 20 and 40. You guys can do the inverse of that and then take the logs of that. So anyway, we will go to the data analysis next time together on this. And we can finish this up. So now we're going to take a break, stop the video, whatever, and we're going to finish, not totally start from the beginning, lab number 6. Now, here's the confusing part. What I want you to do is I want you to go to your handout folder. Nope, I'm wrong. To your homework folder. Try this again. See if I can find it in your homework folder here for a second. I thought it was in your homework folder. Let me see here. Maybe it's under handouts. Labs. Okay, here we go. Go to your handout folder under labs. And it turns out when we were in quarantine, we actually were working on this and we were filling out stuff. So for instance, I'm looking under Anna's right now. And let me see if we have some stuff written or not. If we don't, that's okay. Some of you would have written this in if you're at the lecture virtual lecture, that is. And there it is. Here's some of the stuff we did. So what I want to make sure you have is, can you look in your OneNote, find this page, which is page 9, in OneNote. Right now I'm looking at Anna's, which by the way is everybody's data. We shared data on this. And make sure you put this into your regular notebook on page 8, 9. So put this data onto page 9. Okay. And then we'll go to the next video, which will be over lab 6. So this is the end of the video for experiment number 5. And we'll go to experiment 6 on the next video. So before you get to that experiment though, look up in your handouts folder, this lab is under the guise of labs, and then find this page so you can put in the new data, which is in red. You probably have the old data already. Then we're going to do some crunching of it for the next video.